Mechanics of Fluid, Part 1. In this part, we will discuss three main subtopics: fluid density, buoyancy, and Archimedes' principle. First, let's define what a fluid is. A fluid is a collection of molecules that are randomly arranged and held together by weak cohesive forces and by forces exerted by the walls of a container. Next, we have density. The density of an object, denoted by ρ, is defined as its mass m per unit volume, or ρ equal to m over v. Density is a scalar quantity and its dimension is given by ρ equal to m over v equal to mass per unit volume. It is scalar because of there is no direction for density. Density describes how much mass is contained in a given volume, and this property does not vary with direction. Whether you measure density in one part of a substance or another, it does not have a direction that affects its value. Next, the dimensions of density are mass per unit volume, reinforcing that it is derived from two scalar quantities, which are mass and volume, thus density inheriting their scalar nature. The SI unit for density is kilogram per cubic meter. For instance, the density of water is 1000 kg per cubic meter. This means that every cubic meter of water has a mass of 1000 kilograms. For example, if we have 3 cubic meters of water, its mass will be 3000 kilograms. Likewise, for gold, the density of gold is 19,300 kg per cubic meters. This means every 1 cubic meter of gold has a mass of 19,300 kg. Hydrostatic pressure is defined as the normal force per unit area. The formula is P equal to F over A, where P is the pressure, F is the normal force, and A is the surface area. It is a scalar quantity and its dimension is mass per unit length per unit time square. The SI unit of pressure is Newton per square meter or Pascal, and it can be converted in various other units like 1 Newton per meter square is equal to 1 Pascal, or 1 atmosphere equal to 1.013 times 10 to the power of 5 Pascal, or equal to 1.013 bar, or equal to 14.70 pounds force per square inch. Relative density is a measurement of the density of a substance with reference to the density of water. As we can see from the formula, relative density is the ratio of the density of a substance to the density of water, which we can write as ρr equal to ρs over ρw, where ρw is 1000 kg per cubic meter equal to 1 gram per cubic centimeter. For example, if the density of gold is 19,300 kg per cubic meter, then its relative density will be relative density equal to 19,300 kg per cubic meter over 1000 kg per cubic meter. So the relative density that we obtained for gold is 19.3, meaning 19.3 times denser than water. Note that there is no units for relative density. The force exerted by a fluid on a submerged object at any point is perpendicular to the surface of the object as shown in the figure below. The force exerted by a static fluid on the walls of the container is perpendicular to the walls at all points and increases with depth. In a simple understanding, this force increases with depth. The pressure in a fluid increases with depth due to the weight of the fluid above. As you go deeper into the fluid, there is more fluid above that point exerting a downward force due to the gravity. Variation of pressure with depth. Consider a thin element of static fluid mass m as shown in the figure below. The element of the fluid is in equilibrium because the fluid at rest, which means the net force acting on the fluid element is zero. This can be expressed as F equal to 0. Then substitute F equal to F2 minus F1 minus mg equal to 0, where F2 equal to P2A, F1 equal to P1A, and m equal to ρv equal to ρAh. Then from F equal to F2 minus F1 minus mg equal to 0, from this equation we can derive the following to get the final equation, which is P2 equal to P1 plus rho hg. If in the case of d equal to 0, which means depth is 0 or there is no distance below the surface or the fluid like a figure below, so we can conclude it as P1 equal to P no equal to atmospheric pressure. Hence, the pressure P at depth h below the surface, P2, in a liquid is given by P2 equal to P1 plus rho hg or P equal to P no plus rho hg, where P no is the atmospheric pressure, rho is the fluid density, g is the acceleration due to the gravity, and h is the depth. Let's consider an example. To find the pressure at a point 100 meters below the surface of water, we use the formula P equal to P no plus rho gh. Given that P no is 1.013 times 10 to the power of 5 Pascal, rho is 1000 kg per cubic meter, g is 9.81 meter per square second, and h is 100 meters. The pressure at this point is approximately 1.081 times 10 to the power of 6 Pascal. As for the basic principle of the fluid mechanics, the first one is the pressure increases with depth. In a fluid at rest, the pressure increases with depth due to the weight of the fluid above pushing down. Next, the pressure is the same at any 2 points at the same level in the fluid. At a given depth, the pressure is uniform throughout that horizontal plane within the fluid. This means that if you are at the same depth, the pressure will be the same regardless of where you measure it, assuming the fluid is incompressible and there are no additional forces acting on it. Next, the shape of the container does not affect pressure at any point of the fluid as shown in the figure below. The pressure at a specific depth is determined solely by the depth of the fluid and the fluid density, not by the shape or size of the container. Therefore, whether the container is wide or narrow, the pressure at a specific depth remains the same as long as the height of the fluid above the point is the same. For example, we can see points C, D, E, and F are on the same depth. So, PC equal to PD equal to PE equal to PF, while PS is equal to PT, because point S and T are at the same depth. Thus, we can conclude that pressure at point S is larger than pressure at point C. The figure illustrates the variation of pressure in different materials, specifically 3 liquids labeled A, B, and C. The pressure at point P1 within liquid A is given by P1 equal to PATM plus rho A GHA, where PATM is the atmospheric pressure, rho A is the density of liquid A, g is the acceleration due to gravity, and HA is the height of liquid A above point P1. Moving deeper into the container, the pressure at point P2 within liquid B is calculated as P2 equal to P1 plus rho B GHB, where rho B and HB are the density and height of liquid B, respectively. Similarly, the pressure at point P3 within liquid C is given by P3 equal to P2 plus rho C GHC, where rho C and HC are the density and height of liquid C. This stepwise approach demonstrates how the pressure increases with depth, accounting for the contributions of each liquid's density and height above the point of measurement. So, if the liquid is open to the atmosphere, thus P1 is atmospheric pressure, PA, and P2 is a pressure, P, at a depth h below a point in the liquid. Therefore, P minus PA equal to rho GH, which we can derive to get the equation of P equal to PA plus rho GH, where P equal to absolute total pressure, PA is atmospheric pressure, and rho GH is gauge pressure.